Okay, welcome everybody to the INQA seminar for the 14th of January 2025. And it's my great pleasure today to welcome the speaker, who is Antonio Trovato, who is from the University of Salerno. And Antonio will talk to us about reformulating regression test suite optimization using quantum annealing, an empirical study. So, Antonio, over to you.
So, good evening to everyone. It's a great pleasure to be here. I'm a PhD student at University of Salerno, and today I'm going to present our recent work entitled Reformulating Regression Test Suite Optimization using Quantum Annealing, an Empirical Study. So, first of all, what is regression testing? Well, as we all know, software systems, especially nowadays, undergo continuous modification and enhancements because customers and users have always high expectations about the performance and quality of the software we produce. But we should know that every change, even the smallest changes, can introduce big defects into the already existing components of the system. So the regression testing has the precise aim of verifying whether previously developed and tested components behave as expected after a change that has been made. So let's make an example. For example, let's say that a developer starts with a system with only one feature and the corresponding test T1. Then after some time, he produces a new feature number 2, with the corresponding test number 2. Here, this version, the regression testing would consist of running the test for the feature number 1 to verify whether, of course, the previously already developed feature continues to work correctly. And after some time, let's say that he produces a third feature, so he will launch the regression testing on feature number 1 and feature number 2. So we can say that each time a developer makes a change, regression testing is executed. But just here from this picture, we can understand that for real-world scenarios in which we have large-scale software systems, an ideal regression testing, which consists of rerunning the whole regression test suite, not only is very costly, but generally is impractical. So we must apply some test suite optimization strategies, in part to reduce the effort of regression testing. In particular, I focused my work on test case selection. What is test case selection? Test case selection is an optimization algorithm which focuses on selecting a minimal subset of a test suite to verify whether a modified impacted components of a program continue to work as expected after a change involving other components. This unmodified impacted part is really important in this definition because test case selection follows a previous phase of analyzing through, for example, graph-based approaches, dynamic programming, and so on, an initial phase of impact analysis of the modification, which means that after a change, we initially understand which are the components of the software unmodified that were impacted directly or indirectly by the modifications. Once we have spotted this component, we obtain the corresponding tests, which form the initial regression test suite, which we aim to optimize with test case selection. So it's kind of a modification-aware approach to the test suite optimization problem. We can treat this optimization problem as a single objective problem, so which returns a specific subtest suite as a solution, or as a multi-objective optimization problem. Regarding the multi-objective test case selection version, being a multi-objective optimization problem, the goal is to build a Pareto-efficient subset of the starting regression test suite, leveraging different selection criteria and given a set of the impacted unmodified components that we want to test. So if gamma is the starting regression test suite that we want to optimize, and we have a set of objective functions which mathematically formalize the selection criteria, test case selection aim to select a subset gamma first of gamma to be the Pareto optimal set concerning of gamma concerning the objectives in F. In particular, a solution X is said to be Pareto optimal if and only if it is non-dominated by any other solution in the search space. Or the non-dominated solution form the Pareto optimal set, which Pareto vectors gives us the Pareto frontier. Traditionally, multi-objective optimization, multi-objective genetic algorithms are very well suited in solving multi-objective optimization problems. In particular, in the context of test case selection, Panicale et al. Introduces DIVGA, which improved the older NSGA2 and VNSGA2 algorithms for test suite optimization by periodically injecting individual which are orthogonal to the best individual of the current population of the genetic algorithm. But we must say that not only MOGAS, but also greedy algorithms, in particular the additional greedy variant of greedy, which solves multi-objective genetic algorithms, are very well suited for this kind of optimization problem. But there is no clear winner between MOGAS and additional greedy. And also the great problem with this kind of algorithms, traditional algorithm, is the computational complexity that makes them unfeasible for real world scenarios. And that's why we decided to enter the quantum realm. In particular, also, one of our aims was also to applying quantum algorithms to investigate the effectiveness of applying quantum algorithms for solving software engineering problems, because they haven't been investigated enough, and we wanted to make our contribute in closing this gap. In particular, we decided to apply quantum annealing, both because it has less limitations in terms of numbers of qubits, but also because it is extremely suited in solving this kind of optimization problem. In particular, in quantum annealing, the problem is translated into a problem Hamiltonian whose ground state encodes the solution of the optimization problem and whose variables are mapped into a quantum system. And following the adiabatic theorem, quantum annealing initiate the system in a ground state of an easy to compute initial Hamiltonian, and then slowly evolves the system to reach the ground state of the corresponding problem Hamiltonian. Since we decided to use the D-wave annealers, we also used as a model to formalize the problem Hamiltonian, the de facto standard for this kind of formalization of the wave, that is the QBO model, which formalizes which formulates an optimization problem using an n times n upper triangular matrix Q and of weights and a vector x, each of binary variables. Each of the binary variables are translated into qubits of the quantum system, whereas the diagonal terms of the matrix Q consists of the strength of the single qubits, while the off-diagonal terms are the strength of connected linked qubits. Regarding the state of the art of quantum annealing for test suite optimization problem, when we started our work, it was composed by only BootQA. In fact, BootQA was introduced by Wang et al. And it solved test suite optimization problem and circumvents the limitations of quantum annealing using bootstrap sampling. Bootstrap sampling is a decomposition strategy which, starting from the initial whole regression test suites, it decomposes the test suites in m sub-problems of size n to make each of the sub-problems solvable directly by the advantage system QPU. That is the QPU of the wave that BootQA uses. Once all the m problems have been solved by the QPU, all the solutions are merged into one final solution. But the problem with this approach is that the bootstrap sampling samples the n test cases of the m sub-problems totally randomly. And this led to a set of problems First of all, it is really, really hard to configure. We spent much more time configuring it than actually using it. But also, this randomic nature of the bootstrap sampling doesn't guarantee that we would have an adequate test case coverage. So, for example, between the different subproblems, we could have copies of the same test case, for example. And also this lead to unstable results from execution to execution. We could have totally different results and also unmanageable result because we cannot focus on an objective instead of a selection criteria instead of another. That for software engineers, it's pretty important. So we decided with all these problems motivated us in developing our own solution using quantum annealing for test case selection that we simply called SELECTQA. Our goal was to develop a new approach that could be at least as effective as traditional state-of-the-art methods, but efficient enough to be applied in real-world scenarios. And so our research questions were, is SELECTQA more effective and more efficient than the traditional state-of-the-art and bootQA methods? So what we had to observe here is that while the traditional state-of-the-art methods formalize the optimization problem as a multi-objective optimization problems, which means that they produce for each execution a Pareto frontier. On the other hand, bootQA formulates the optimization problem as a single objective optimization problem, which means that for each execution, it outputs a single subtest suite, a single solution. And not only this, but also the selection criteria were different. In fact, the traditional state-of-the-art traditionally used a selection criteria, test cases cost, past fault coverage, and statement coverage. On the other hand, bootQA in its presentation paper uses a selection criteria, test cases cost, and failure rates. So to make fair comparison between SELECTQA and the traditional state-of-the-art and SELECTQA and bootQA, we decided to develop two different versions of SELECTQA. The first version of SELECTQA is a multi-objective version of SELECTQA. That is the one that we had compared with the traditional state-of-the-art. In particular, we decided to build our Kubo problem. We decided to start from an optimization problem of a linear optimization problem with quadratic constraint and translate it into a Kubo model, quadratic unconstrained binary optimization problem. So since the objectives of minimizing the execution cost and maximizing the passive fault coverage could be expressed linearly, we decided to use as optimization function the one with these two objectives. So we expressed the optimization function as a linear function. In particular, here we can see that x with I is 1 if we select the ith test case is 0 otherwise. Cost of tau with I is the execution cost of the ith test case, while E with I is a binary value which is 0 if the ith test case wasn't able to spot a failure in the past, 1 otherwise. Alpha is a weight that helps us to focus on a selection criteria instead of another. Regarding the objective of maximizing the statement coverage, it was a bit more complex, but we noticed that, for example, for a statement to consider it covered, we just need that at least one test case that covers it has been selected. So, for example, if we look at this table, we just need to select tau2 and tau3 to cover all the 4 statements. And starting from this observation, we obtained the first constraint that we see here in the first expression. Here, what we say is that if T with K is the set of test cases that covering the statement K, we just need that at least one of the test cases of this set has been selected. But since we have to apply this constraint to all the statement, and since we want it to be want to bring it up on the initial objective function to obtain an extended final functions with all the three objectives, and since these should be minimized because the objective function is a function that we want to minimize, we converted, we translated that constraint in the second expression that we see here. In particular, in this case, the annealer will tend to select instead of non-selected the test cases, because if it selects the test cases, the difference will be 0, squared will be always 0. Otherwise, if it not select, the difference would be -1, so each time squared would be 1 and 1 and so on. And then we brought the expression up into the objective function, applying also a penalty p that has to balance the values of the third objective with the rest of the objective function. The value of the penalty can be empirically obtained with different methods. We used in particular the upper bound method. So we set the penalty as slightly higher than the upper bound of the initial objective function. Regarding the single objective version of SELECTQA, it was much more easier because both of the selection criteria could be expressed linearly. So we just obtained this linear equation to solve. Of course, also us had to deal with the problem of the physical limitations of the quantum annealers. In particular, we instead of relying on a local decomposition strategy, we decided to rely on the D-Wave hybrid solver service. In particular, we use the portfolio solver version 2, which uses the same QPU of bootQA. The portfolio service receives from the user the Kubo problem and eventually also a time limit t. And on the basis of the complexity of the Kubo problem that it receives from the user, it starts a number of parallel solvers, classical solvers that run on CPUs or GPUs. Each of the solvers have its query module and that continuously send through quantum queries a small portion of the QPU, of the Kubo problem to the QPU, small enough to be solved directly by the QPU, which replies through the query module to the classical solvers about promising regions of the search space to find the optimal solution. Once we arrive at time t, or if all the solvers finish their execution, all of them return their solution, their best solution to the portfolio solver, which selects the best one and send it back to the user. So let's talk now about the metrics and the comparisons between SELECTQA and the other methods. So regarding the multi-objective version of SELECTQA, we ran DIVGA and SELECTQA 10 independent times. For additional greedy, it was useless because it is totally deterministic. And in particular, we ran the 3 algorithms over 4 GNU open source programs, Flex, grep, JZip, and SET that were the programs used in the original paper of DIVGA. Now, actually to make the real actual comparison between multi-objective optimization algorithms, which returns Pareto frontier, we should compute the actual Pareto frontier and see which of the algorithms produce the Pareto frontier that is the nearest one to the actual Pareto frontier. But computing the Pareto frontier for such a complex problem is unfeasible. So we made another kind of a posteriori evaluation, building a reference Pareto frontier that is composed by all the non-dominated solutions obtained by between all the frontiers obtained during all the runs by the 3 algorithms. And the metric that we computed was for each of the algorithms the number of the non-dominated solution that was taken to build the reference Pareto frontier. And to obtain statistically reliable results, we tested this metric using the Mann-Whitney U-test and the A12 effect size. Regarding the efficiency metric, we used the mean total runtime over the 10 independent runs. In particular, we have to say that for SELECTQA, we use the output runtime, the runtime that is an output of the HSS service of the wave. This metric consists in the total runtime that the portfolio solver needed to solve the whole problem. We also, this metric was tested, we statistically tested also this metric with the same tests. And here we can see the results of the comparison regarding the effectiveness of the different strategies. In particular, we can see that in 2 out of 4 cases, SELECTQA won. Whereas in 1 out of 4 the cases, the IVJ was the best, and in the other case, the best was additional greedy. And as we can see in this graphic, for the seed program, for example, the majority of the non-dominated solution found by SELECTQA was selected to compose the final reference Pareto frontier for the seed program. Regarding also the statistical tests confirmed the results we obtained regarding the efficiency, all with large effect size. Whereas regarding the efficiency comparisons, also here, SELECTQA won in 2 out of 4 cases. In the other 2 cases, additional greedy won. But we have to consider that additional greedy, as I said at the beginning of the presentation, does have high computational complexity, which makes it unfeasible in real-world scenarios. So, in fact, he won in 2 programs that were the smallest one. On the other hand, SELECTQA performed constantly, regardless of the size of the problem, and also these results were statistically confirmed by the statistical tests. So regarding the comparison between the single version, single objective version of SELECTQA and BootQA, also here we ran 10 independent times both the algorithms, and we used the datasets that were used in the presentation, the original paper of BootQA, that are paint control from ABB Robotic Norway and GSD-TSR from Google. Now, since both the approaches in this case solve a single objective optimization problem, so for at the end of each execution they return actual solution, an actual single subtest suite, we directly compare the test suite, the returned subtest suites, in terms of the objective, the selection criteria of the problem, that were the execution cost and the failure rate. And we statistically analyzed the values of these 2 objectives using always the same statistical tests. The metric, the efficiency metric is the same as before. We just have to say that regarding BootQA, the execution, the total runtime for a single execution is given by the sum between the local classical decomposition time and the execution time of the advantage system QPU. And we also statistically analyze these results. Regarding the effectiveness for paint control, SELECTQA was able to find, it seems that SELECTQA found just one solution, was run just one time, but it found always the same solution for each of the 10 run in each of for both the datasets. In fact, it seems to be the actual best trade-off between execution costs and failure rates. In particular, for paint control, SELECTQA was able to dominate the solutions of BootQA in 10 out of 10 cases, whereas for GSD-TSR, SELECTQA was dominated in 8 out of 10 of the cases, the solutions of BootQA. In only 2 cases, BootQA found a solution that has lower execution costs, but also lower failure rates. The statistical tests also here confirmed the results that we have obtained. And regarding the efficiency, BootQA is definitely the one to beat. Because it is really, really, really fast. In fact, this happens because the decomposition with nowadays computer is very, very easy. And the problems that the QPU has to solve are, of course, really, really tiny. So BootQA is really fast, and the statistical results confirmed the statistical tests confirmed the results. So in conclusion, SELECTQA reached the goal of proposing an approach that could be as effective as the traditional state-of-art methods, but much more efficient and so much more usable in real-world scenarios. Nonetheless, BootQA remains totally unbeaten in terms of efficiency. Talking about future works, we of course have plenty of work to do. First of all, we want to extend our comparison also to another algorithm that for another quantum approach to test suite optimization problem, that is IGDAC QAOA. And also we'd like to expand our study over larger programs and larger datasets. But in particular, we are currently exploring also the potential of clustering decomposition strategy, and also we are trying to understand the potential of combining the clustering decomposition strategy with a QAOA-based approach. We already obtained some preliminary results that show that QAOA algorithms that we tested with different noisy and ideal environments. So we at the moment currently we didn't already use the actual quantum computers, but we just simulated them. But or the preliminary results that we obtain applying QAOA with clustering strategies show that not only QAOA was able to outperform the traditional state-of-the-art method, but in particular, in terms of efficiency, this strategy was comparable with the BootQA method. So the preliminary results are really, really promising. And thank you for the attention.
Many thanks, Antonio. Lots of interesting things for the audience there. Are there any questions? Any member of the audience, either raise your hand or unmute yourself and speak up. Maybe I can start with the first question. So I'm trying to get a feeling for how big these problems are by comparison with the number of qubits on the Advantage chip, for example, which I believe is 5,000 approximately. So how many you're using the D-Wave hybrid solver, which I guess is a sensible approach. Do you know how much bigger is your problem than the 5,000 qubit native chip?
Well, they are really, really complex. In fact, when, for example, when I was developing it and I made the program print the whole Kubo model, the whole Kubo model, it was really huge because there are a lot of variables, because the test cases generally are also in the order of the thousands and thousands of test cases, but also the connections between test cases, because in the case of maximization of the statement, the connection was made by more different test cases that cover the same statement. And this connection between test cases are a lot and really and make the model really, really, really complex. And so, yeah, the problem is very big, and there is the need of classical decomposition at the moment is mandatory, because current quantum machines cannot solve them alone. And so the point, yeah, sorry.
As part of that same discussion, I noticed that you had a quadratic constraint at one point.
Yeah.
Which presumably
Yes.
you need
For the maximization of the statement coverage, I inserted it there because the idea is that if I can, maybe I can show it again. So it was there. So here is the idea, for example, in this table is that, for example, there are some common statements that are covered by different test cases. So first I started with this constraint that says I need that at least one of the test cases that covers the statement K is selected. Since we have to repeat this for all the case statement, but also since I need an expression, what I needed was an expression that I could insert in the initial equation to obtain that can express the connection between two test cases that cover the same statement, that at the same time also I want to minimize. And so that's why I come up with this, because in this case, for example, if I select the same, if I tend to select test cases, I would have here 0. Otherwise, if I tend to not select the test cases, this summation would be much more higher. And that's something that the annealer wants to avoid. So that was the sense.
But terms of that form are famously inefficient when you try and put them on the quantum annealer, because this becomes all-to-all coupling between qubits. So I was wondering whether you had tried to replace this quadratic constraint with a linearized version of that constraint.
Yeah, yes, that's absolutely a point because it makes it much more complex. And actually, we are also working on reformulating again the problem. In particular, now that we are working, as I said, also on QAOA, that was definitely one of the ideas. Also because we have obtaining great results with combining it with clustering. And the big amount of connections between qubit can also make it much more difficult for the annealer to solve the problem. So yes, definitely this is one of the paths that we have to we are considering. Yeah, definitely.
Good.
Totally.
Any other questions for Antonio? Well, if not, let's thank Antonio once again for a very nice presentation. A round of applause from me.
Thank you. It was a great pleasure.
And a very enjoyable presentation. And I shall finish there. And I look forward to seeing everyone at next week's INQA seminar. Thank you very much. Bye-bye.
Good evening to all.